Okay, so we begin our second lecture on unsupervised learning. Last time we talked about how unsupervised learning is a type of learning different from supervised learning, different from reinforcement learning, and it involves dealing with lots and lots of data, unlike in the other two topics. And we said there are numerous applications to unsupervised learning, numerous examples, and so on. And so today we'll actually begin with some specific algorithms for unsupervised learning. First of which is for clustering. That is, if you have given some data in some kind of multidimensional space, and we are told that there are going to be 10 classes in this one. Can you find me the 10 clusters of this data? So in a way, if you do that, you are able to automatically segregate the data into 10 parts. And if, with a few samples, which is called semi-supervised learning, we can figure out that, okay, each of them corresponds to a certain class. So that way your labeling is all done. So that kind of work is taken care of with unsupervised learning. So clustering is the topic. And this is really the most famous unsupervised learning problem. Autoencoders is another one. And so let's begin this topic, and I'll share my slides on this topic on k-means clustering, it's called. Okay, the topic is k-means clustering, which means we have k is simply some number. Means two uses of the word means. It is mean in the sense of a parameter of a normal distribution, the mean of a normal distribution, right? I mean, not necessarily normal, but typically k-means is looking for a normal distribution. Uh, and mean is every distribution has a mean and a variance. Supposing I've given you a mean, which is the first moment is also called as first order moment. So we need to find those means, and also ideally we'd also not only find the means but also find the variances of the individual clusters that we find. Clustering is simply means finding groups, right? Groups of data. Every group is referred to as a cluster. So this is actually a topic in a bigger topic called topics in mixture models and expectation maximization. That's a bigger topic. K-means is just a very specific part of this, a simple algorithm for dealing with mixture models, and as a starting point for a more sophisticated method called expectation maximization. So the topics here are, we kind of look at what are mixture models, what is k-means clustering, and specifically deal with mixtures of Gaussians. And then we talk about the expectation maximization algorithm, and then refer to Bernoulli mixture models and infinite mixture models. So what is the k-means clustering problem? It is the task. Given the data set x sub I equal to 1, we are given n data points in d-dimensional Euclidean space, okay? Typically it's Euclidean space. I guess it has to be more modified if you want to have some discrete space. Partition into k clusters, which is given. What is k is given. So so for this, we use what's called one of k coding. Okay, that's the same idea we've looked at before. Look at this data over here. We're given this data in a two-dimensional space and asked to label, let's say k equal to 3, we're asked, can you label these points as coming from 1, 2, and 3? There's some overlap. We can say, well, looks like there are 3 elliptical clusters here. There's been some overlap. They'll have their own means, and we'd find the means of these clusters, and also we'll get an assignment to every point saying which cluster it belongs to. We're saying there's 1, 2, 3 clusters, and we'd color each of these points saying this is a red, green, blue, let's say. And the clustering task is to find what is the class each point belongs to. That is the task. So we can think of an indicator variable R and K belonging to 0, 1, where K equal to 1 through K, right? This is sub K here. It belongs to one, how many classes? Like here, 3, right? So we would say Rn3 uh, describes which of K clusters the data point Xn is assigned to. So Xn is just, this is the initial data points. They're simply labeled 1 through N, capital N. And so a small n would be the value that goes from 1 through N. So we're saying, let's say it's a point number 5, if and we could run it through, and we would say 5 3 belongs to say 1, indicating that yes, that is true, but 5 1 or 5 2 would be 0. So that's one way, having an indicator variable that is telling us which cluster each point belongs to. And we'd be using here one of K coding, in that we are saying that the K value determines whether it is 1 or 0. Yeah, it is not quite one of K where we have a vector representation. All right, so this is slight variant of that. Okay. So we can think of an object. So how are we going to do this? How are we going to assign these points to different classes? So this is some kind of an optimization problem. It's a fairly simple optimization problem. The objective function, we can say, is the criterion function j, n goes from 1 through capital N, k goes from 1 through capital K, R and K, which is we are running through all the n samples and all the 3 classes. R and K will be 0 for a lot of them. But when the point belongs to a class, that's going to have the value 1. And this one is saying xn minus mu k squared. Mu k would be the mean of the kth class. There is k is what? K equal to 1 through 3, for example. That would be the mean for the appropriate class, and we take the appropriate point xn here, and we try it and minimize the distance. So this is saying that we should assign these we should find the means, and not only that, this point should be closer to that mean than to some other mean. That's what this is saying. So, and we sum over all the points here and all the classes here. So this is really sum of squares of distances of each data point to its assigned vector mu k. All right, so it's becoming a little more sophisticated than simply labeling. This is saying we should label it in this way such that this quantity is minimized. Goal is to find, so what is the goal? Is to find values for R and K, which points belong to which class. That's what this is saying. Is the 5th point belong to the class 1 or class 2 or class 3? We need to know what is the value of R and K. It's 0 or 1. And the mu k, so we also are not given the mu k's. We need to find the mu k. And so we choose these so as to minimize this quantity j over all of the points. And this again, we resort to an iterative procedure. And because the objective function is a linear function of R and K, optimization can be performed easily to give a closed form solution. I see. So this can have a closed form solution. And so let's see how that goes. Each iteration has 2 steps: successive optimization with respect to R and K and mu k. So we need to have, we have a one step to assign the R and K and another step to assign the mu k. So there are 2 updating stages. First, choose the initial values for mu k. And then the first phase is to minimize j with respect to R and K, keeping mu k fixed. So we're saying choose some arbitrary values for the 3 means. We don't know. or maybe we have a rough idea where the means might be. We just pick it up. And then you say, run through all your R and K values, as trying out various combinations of zeros and ones to them. And which value is going to minimize J. After that, you've got an assignment now. So basically what it's saying is pick those means and then see as to which one is each point, which is the closest mean that it gets to, and you assign it to that particular class, 1, 2, or 3. Second phase is to minimize J with respect to mu K, keeping R and K fixed. So second phase says, well, recompute the mean for that set now that you have assigned them to a particular class. What is the mean of that set? And then go back, and because now you have found hopefully a better mean than what you had earlier on, because it was computed based on the assignments of these points. And then we iterate back and forth, right? We first phase minimize J with respect to R and K, second phase minimize J with respect to mu K. Roughly these two stages correspond to what's called as the E step of expectation maximization and the M step of expectation maximization. So we are saying what is the expected assignment of R and K? So we are choosing the best possibility by looking at which is the nearest sample. And the second part is that of the maximization, or in this case, minimization of the value of J uh, and with respect to mu, keeping the R and K fixed. So this step does the expectation of the R and K, and this step does this step keeping R and K fixed and finding the value of mu. So what is the maximum likelihood estimate for the mu, that kind of a thing. That's what we're doing here. Expectation is what is the expected class? Data point, which class will go to the expected class? Maximization, what is the maximum likelihood estimate of the mean, right? So this is a useful thing to keep track of, because when we get to expectation maximization, it gets a bit confusing. What are you doing in the two steps? One is expectation maximum. What does it mean? So this is a very good analogy to think about, is what is the expected class for each data point, the missing data. And the second one is computing the parameter. So determination of the indicator R and K, because this is a linear function of R and K, this optimization is performed easily. Okay, finding the R and K is easy. Terms involving different n are independent. Therefore, we can optimize for each n separately. And choosing R and K to be 1 for whichever value of K gives minimum value of xn minus mu K squared. Does R and K equal to 1 if K equal to arg min x minus mu J, 0 otherwise? Well, all this is sounds pretty complicated, but all it is saying is assign xn to cluster whose mean is closest. So you've got some value of mu's, and simply take your points, measure the distance to each of these means, and simply give it the label to whichever mean was closest. But that has to be said in this way. What do you mean closest? Closest has to be argued as arg min J over all of the means here. And so R and K is equal to 1. And so that picks up the value of J here, min over all of them. And that is the value of K, and then 0. So it becomes 1 or 0. Anyway, all of this is a complicated way of saying the same thing, of assign the point to the closest mean. Optimization of mu K, the M step, the second step is to hold R and K fixed. Objective function is a quadratic function of mu K, minimized by setting out derivative, right? Optimize, setting derivative of this quantity with respect to mu K to 0. So if we take the derivative of this with respect to mu K, the 2 goes outside, comes over here, which is solved to give mu K is equal to sum R and K xn divided by this quantity. And what it is saying is, take all the points that you have just assigned to that cluster and find the mean, set mu K to the mean of all data points assigned to that cluster. This is how many, the summation is simply how many points are in that cluster, that is the denominator. And this is determining the R and K values. So that determines together the value of the mean. So this says equal to number of points assigned to cluster K here. And this is how we obtain the value of mu K as RNK. So the xn comes into play. RNK is 0, 1. Xn is the value. So this is simply saying add all the values together and divide by the total. That's what the mean is, right? If I give you a set of numbers and ask you to compute the mean, you'd add the numbers and divide by the total number. Total number is given by the denominator here, and add whichever samples are in that cluster. That's what this RNK is doing. And we're simply adding all the samples together. So that's why it gives us the mean, right? So intuitively, it's the most simple algorithm, but mathematically, it looks a little complicated. So termination of key means, how long do you go? Two phases: reassigning data points to clusters, recomputing the means of the clusters, done repeatedly until no further change in assignments. And since each phase reduces J, convergence is assured, may converge to a local minimum of J. So once again, it may not be a global minimum, it gets to a local minimum. There is an interesting data set that comes from the Yellowstone National Park in the United States. There is a geyser over here. It's called Old Faithful, and this one suddenly spurts from the ground up. It goes up like a fountain for a while, and then it stops, and then it waits for a while, and again it goes up. So it's a natural fountain. And and then they are plotting data. So the Old Faithful data set has an x-axis corresponding to the length of the spurt, and the y-axis is the duration between spurts. All right. So they collected this data set, saying, okay, somebody sat with a stopwatch or something and looked at how long the water is spouting, and then it stops, and then how long it takes to come back up. And then they found the data looks like this. You see all the green points here? The data looks like this. So then they're asking the question as to, oh, okay, this is the data. There's nothing else given. It's just the data that is telling us we have an unsupervised learning problem. And by visual inspection, we can say it looks like, we can try and do a Gaussian. Maybe we should have a Gaussian for it. Single Gaussian would fit like this. The best Gaussian would look like this. Maybe a better fit would be a mixture of two Gaussians, saying there is one Gaussian here, there's another Gaussian here. So the data seems to fit in the sense it's either this type of a spouting, this type of a spouts it is, or another type of spout it is. So there are two types of spouts. It all based on, I suppose, geothermal under the earth and that kind of thing. And so this would fit two Gaussians, one Gaussian here, another Gaussian here. So you could try k-means for this, which would say that we start out some arbitrary values. Maybe we look at the data and give it some centers for these, and then let it keep going, and it will compute the mean of each set of points that are closest to that point you just gave. And so that way it labels every point as to which cluster it belongs to and what is the mean of that. So this is solved using k-means, or in this case, two means. So this is an interesting diagram which shows what happens with each iteration of the k-means algorithm. So they took the Yellowstone old, it's called that particular water spout is referred to as Old Faithful, right? Apparently it just keeps coming like that. I don't know, for thousands of years. So it's a really faithful geyser. And so they are trying to cluster these 2 points. And this is thought of as we need to find the two means. And they purposely chose a starting point, this blue X here and the red X here. And if you give that and you perform the E step on it, E step simply takes these points and assigns them to the closest means. It's that would be equivalent to drawing a line between the red X and the blue X and drawing a perpendicular bisector to that. That's what this line is. This pink line is a perpendicular bisector to the line joining the two X's. And simply saying the points on the left side of the perpendicular bisector are all now blue, and those on the other side of the line are all red. So that is the first initial step. So because of the fact we are measuring the distance to these points, so anything on this side of the line is going to be closer to this, right? That's the argument. The perpendicular bisector will make sure that these points are closer here. So that is the first step. And then the M step would say, well, okay, if these are your clusters, give me the means for the two clusters. So the mean for these red points turn out to be this X here. And the means for these blue points turn out to be this X here.
Professor, you're muted if you're speaking.
Muted here. All right.
And we couldn't hear for the last couple of minutes what you were saying. There was lag.
Oh, there was a lag. Okay, maybe my internet connection or something. Okay. All right. Can you still see the slides?
No, we can't.
Oh, okay. I need to. Okay, the whole thing got cut for a short period of time. Okay. Okay, can you hear me now?
Yes, we can hear and see you.
Okay, this is actually a very interesting slide. I suppose I should go over it again. This is fairly obvious, but we are given these green points and we are starting out with arbitrary two means here. And the E step would be to assign these points to the closest mean. And it is being done here by drawing a perpendicular bisector to the line joining these 2 points. Anything on one side of the line is labeled blue, and the other side of the perpendicular bisector is labeled red, because that's the Euclidean distance closeness. And we compute the means for the red points now and the blue points as being these two, which seem to be a better estimate for the two clusters than the earlier ones, which was way off. So we again repeat the E step, which says, okay, draw the perpendicular bisector between these two, and which is this one, and say assign the points to the closest ones. Ah, look at that, already we're getting a good assignment to the points here and a good assignment to the points over here. And the M step again is recomputing the means of them. And so the means that moves these x's here to the corresponding ones. And again, we do another E step and another M step and another E step and another M step. The finer clusters and the means would be these two are the two means, and these are the missing data assignment, if you would. That is, we did not have the cluster to which it belongs to. That's like a supervised signal type of thing. That's what it has learned over here, saying these points belong to this cluster and these points belongs to the other cluster. All right, so this also shows the cost function after iteration. We said this is all based on a cost function J. It's interesting to make a plot of after iteration. So after iteration 1 of the EM step 1, 2, 3, 4, and they are plotting the value of J here. And I think they're showing that these correspond to the E step, M step, and so on. Poor initial value chosen for cluster centers, several steps needed for convergence, and a better choice is to assign mu k to a random subset of k data points. They purposely chose some poor initial values, so it takes a longer time. But another way is to assign mu k to a random subset of the k data points. And k-means itself is used to initialize parameters for Gaussian mixture model before applying EM. So actually the k-means is a simple clustering algorithm, but we saw some examples, I think I showed last time, the Mickey Mouse data. It turned out it was not doing that nicely. For example, the face should have been one cluster and the ears should have been the other two clusters. And it is kind of mixing them up. EM is okay, but you could do better than that. Faster implementation of k-means. Okay, even the k-means can be improved. The direct implementation of k-means can be slow, and in each step, Euclidean distances compute between every mean and every data point. So you have to again and again, if you have a large number of data points, then you have to compute the distance for every point. So faster implementation exists, pre-computing trees where nearby points are on the same subtree and so on. So there's some clever algorithms available for k-means. You're implementing k-means for this project too. So there's an idea. You can look into how you can improve the speed if that's being very slow. There is also an online stochastic version where we take a point at a time and keep on improving. Instead of batch processing the entire data set, you're not taking the whole data set, you're adding one at a time. So you keep getting updated versions of it from the old versions by is a learning rate again, and x came. So this looks like so much like gradient descent type of problem, and we are taking the data and looking at the distance to the mu old and updating it to mu new. So this would be equivalent to uh, the k-means algorithm with a stochastic online version. And Euclidean distance itself has limitations, inappropriate for categorical labels. So in which case we are using with data, not necessarily continuous data, use more general dissimilarity measure nu of x prime. So instead of saying take the Euclidean distance, squared Euclidean distance between the point x and the mean mu k, you could say, well, do you have some kind of a dissimilarity measure between xn and the mu k? And so we use that, and that would, which gives the k midoids algorithm, it's called. And m step is potentially more complex than for k means. All right, so we have to compute whatever this quantity is. All right, so if k means is so simple, uh, what are the limitations? Every data point is assigned uniquely to one and only cluster. So this says this point only belongs to this cluster. All right, it's like taking handwritten digits 0 through 9, and we are getting 10 clusters out of it. And there might be a peculiarly written 0 where somebody hasn't closed the loop of the 0, and kind of it could be interpreted that it's either a 0 or a 6. So such a point may be equidistant from two cluster centers. And a probabilistic approach will have a soft assignment of data points reflecting the level of uncertainty. So when you have a handwritten digit, which could either be a 0 or 6, we would give it an assignment saying for the cluster 0, it's 0.5, and the cluster 6, it is 0.5. So that's called a soft approach rather than a hard one that says this is a 6 or this is a 0. So isn't that a better thing to be able to have a soft assignment rather than a hard assignment saying can only be one of the two possibilities. So that's what EM actually does that for you. It can be applied for image segmentation and compression, is partitioning the image into regions. Each pixel is a point in RGB space, and there are all kinds of applications. Image segmentation and compression, this can be used. It's a very clever algorithm. K-means can be used, k equal to 2, k equal to 3. So this is some image was given here, And they were clustering these pixel values here into two classes. This is a two different colors. This is three colors here. This has got 10 colors here. This was the original image here. And so they were getting segmenting. So interestingly, you can go about segmenting a whole image. And this is saying that these points are assigned the blue segment, and this is brown and so on, and which is pretty good. The original image was like this, and it is how is that being done? Is each pixel is a point in RGB space. All right. K-means clustering is used with a palette of K colors, and method does not take into account proximity of different pixels, but it is simply assigning a pixel to one of K classes, either two colors or three colors or 10 colors. And each pixel is a point. So each point is in RGB, means in three-dimensional space, you have each of these points, and each of these points have to be assigned to one of three clusters or one of 10 clusters. And then you are saying, okay, then pixel number 78 belongs to red or brown or whatever. So fairly straightforward way of segmentation. So K-means, such a simple algorithm, can be quickly used for image segmentation, which seems like a very powerful use of it. But what is the disadvantage here is that it is treating every pixel as an independent entity. It is not using the fact that some neighboring pixels have some dependence on them, and so that ought to be taken into account and so on. But here it looks pretty good. Okay, and here is another image, and can also be used for data compression. Interestingly, lossless or lossy. K means for lossy compression. So it is not lossless, for a lossy compression. So original image may need 24N bits. RGB need 8 bits each. Compressed image needs 24K plus N log K bits. And all right, so if you, for each of N data points, so in the sense, an image has N data points, one image, and you store only identity of K cluster centers to which it is assigned. So this is a method called vector quantization. It's a very classic method that is used to convert into a representation of the image with a lossy compression using vector quantization. And it compresses the data from the original RGB. Each of them requires 8 bits. That's why you have 24, and you have N of those, so the 24N. And compressed image needs, for K equal to 2, 3, 10, we saw, plus N log K. Compression ratios are for K equal to 2, 3, 10, compression ratio 4%, 8%, 17%. It's not with that great a compression. 17% was the best that was obtained here. Okay, but yet another example from a domain of handwriting styles and so on. I'm going to skip this part. Clustering of handwriting styles is how many, look at this data. How many styles of THs are there in people's handwriting, right? And this is a problem that we encountered in our research. And we actually tried out different methods, and that's all there is. Okay, so that would say, well, okay, maybe there are 4 or 5 of them, and can you tell me which kind of TH it is? Like this one is going up like that. So if you're doing handwriting comparison to say, what is the style of handwriting the person uses, and you could say, well, what kind of TH does the person use? This kind of TH seems very different. Okay, or maybe this is similar to this one here. And another style of TH, which might be more like this. You're first doing a loop like that. This one seems like you draw a cross first. And this one, it says, no, you go and make a loop first and then cross it like that. And so that's an example of that. Okay. All right, then let's, do you have any questions on this topic, K-means? Okay. So let's go to the next topic, which is mixture models. mixtures of Gaussians. All right, so we just finished k-means clustering. So we are on to mixtures of Gaussians. All right, so what is the goal of mixture modeling? And latent variables and maximum likelihood and expectation maximization for Gaussian mixtures. Expectation maximization is a general technique that can be used for whenever some data is missing, you can use that to make an estimate of that. We think of clustering problem as some data is missing. Every data point has some data missing. We're estimating what is that value, which is the which cluster it belongs to. But this is specifically about mixtures of Gaussians. So the data given to you is known to be a mixture of Gaussians, 2 Gaussian clouds, or 3 Gaussian clouds, or 10 Gaussian clouds. And so this is specifically about mixtures of Gaussians. So mixture is how many components are there? So a GMM, or a Gaussian mixture model, is a linear superposition of Gaussian components. So this is a linear superposition. So there is it's a superposition of 3 distributions, P1 of X, P2 of X, P3 of X. And it's a linear combination. There is some weightage associated with P1 of X, P2 of X, and P3 of X. And typically the weightage adds up to 1. So we are taking a combination of 3 of them together. It provides a richer class of density models than a single Gaussian. Single Gaussian is just one cloud, right? We already saw 2 clouds. So that is more appropriately modeled as a mixture model. We formulate a Gaussian mixture model in terms of discrete latent variables. So we are saying that there is a missing latent variable. Latent means we can't see it. And we have a latent variable, which is which cluster does the data belong to. We know the particular value of the data. It's RGB value or its feature value, that is known, but we don't know which cluster that belongs to. We formulate GMM in terms of discrete latent variables. This provides deeper insight into this distribution. Oh, okay. So the mixture model is actually a distribution. So it consists of a combination of distributions, but it is also a distribution. Serves to motivate the EM algorithm, which gives a maximum likelihood to the number of components and their means and covariances. We already saw that k-means does something like this, but now we are putting in the framework of Gaussians. So a Gaussian mixture distribution is written as a linear superposition of k Gaussian components. So what does this equation say? It says we have some variable x, which could be a vector, and we are saying that is a summation of pi k. Pi is just the particular weightage of that particular component. N stands for normal distribution. X is a normal distribution with a mean mu k and a covariance matrix sigma k. So this is a Gaussian subscripted by k, which means corresponds to the kth component. And we are summing k equal to 1 through capital K. So sum of these 3 components is p of x, or 2 components is p of x. And here below we have an example of a data set for X, and we are modeling it by 2 Gaussians here. And so that is saying that P of X is this combination distribution over here, which consists of 2 nice Gaussians underlying it. So we're saying represent K by a K-dimensional binary variable. So this particular K is represented by a K-dimensional binary variable using 1 of K representation. And let Z equal to Z1 through Zk, whose elements are Zk belong to 0, 1, and the summation of these Zks is equal to 1. So there is no Zk here, all right? But we are introducing this latent variable. So K possible states of Z corresponding to K components. So K is the 1 and 2, and the Z corresponds to 1, 0, and 0, 1. So we are representing that K here. So there is a K, and that K is now expanded out as a vector. Previously, it was just a scalar value. Is it cluster 1 or cluster 2 or cluster 3? We're making a big deal out of it. We're saying 1 is represented as 1, 0, 2 is represented as 0, 1. In this case, it's just a binary representation. If we had 1, 2, 3, this would be 1, 0, 0, this would be 0, 1, 0, and then for 3, it would be 0, 0, 1. And 1001. Okay. And then we have pi k is the weightage of the components, like zero point 0.4 and zero point 0.6. So that is the weightage given to these two distributions. Mu k is, let's say, minus 28 is the mean here, and 1.86 is the mean here. I guess the origin is somewhere in the middle here. And sigma k is how spread out are these two distributions, is the standard deviation of the two distributions. And here we are actually giving a color to all the data points in that old, that was not old faithful. There's some other three class data set, k equal to 1, 2, 3, z equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. And we are assigning the points here with a certain shading. You see the colors kind of get mixed up here between red and green and between blue and green, which means we are assigning to these points a confidence as to whether it belongs to green and red. In this case, it might be 0.5, 0.5. And that's why a combination would have a color running in here, so on, rather than hard classification. So we have k corresponding to 3 components and so on here, all right? So the goal of Gaussian mixture model is a linear superposition. Find maximum likelihood parameters, pi k, mu k, sigma k, and examples of data sets. We saw this is a one-dimensional data set, and this is a two-dimensional data set, k equal to 3. Each data point is associated subclass k with probability pi k. So this is saying there is a certain probability pi k associated with each class here, all right? So k equal to 1 through k for each class, for each of the x's here, right, for the x. So, and we're summing over all these values here. So that's where the probability comes into play, the pi k's. So the joint distribution, we define a joint distribution of latent variable and observed variable. So now we have P of x comma z is equal to P of x given z times P of z. We know this from product rule of probability. X is the observed variable. Z is the hidden or missing variable. And P of z is the marginal distribution, P of z, and the conditional distribution is P of x given z. So there is a, given that class z, what is the distribution of x? So this is, we formulate the problem in this way. And here is a graphical model representation of the joint distribution of P of x and z is represented in the form P of z times P of x given z. This can be written in a graphical model. Z is this first term here, is this first variable. This is x given z with a directed arrow here, indicating the parent-child relationship of these variables. Given z, what is the distribution of x, right? Observed variable. So specifying the marginal P of z is being represented here by means of the probabilities pi k, P of zk equal to 1, we are associating a probability with that, whereas sum of all these pi k's is equal to 1. So we say for the whole vector z, it's a product of, so this gets into the one of k representations, and we have to multiply all of these pi k zk. It's a little bit messy to keep track of all of this. With one component, P of Z1 equal to pi 1 of Z1, with two components, Z1, Z2, which is two clusters. We would have pi 1 Z1, pi 2 Z2. Specifying the conditional probabilities. The conditional probabilities are Gaussians here. And then specifying the marginal distributions. Okay, those are all being plugged in here, the standard form of a Gaussian mixture. And then the introducing the latent variable, some kind of a viewpoint of that. We have found a formulation of a Gaussian mixture involving explicit latent variables. Of course, we saw that this is p of x comma z over the z is p of x. And so this gets more complicated. This leads to a definition of responsibility and a conditional probability. Responsibility associated is given here, where we end up having some kind of a normalization term here to make it probabilities associated with each of the classes. All right. So we can think of P of zk equal to 1 equal to pi k, and then that is being viewed as a prior and posterior probability. And so this is getting pretty complicated. Next, we look at how to get data from a mixture model synthetically, and then given data set, how to model the data using a mixture of Gaussians. So this is a data set, and we have a complete data set, and here is an incomplete data set. Complete data set is the points are all assigned values. So they synthesize data from a mixture. So their initial data was like this, and use ancestral sampling, and start with the lowest number node and draw a sample. So this is a kind of sampling method to generate the data. This is talking about how do you get this data set. They started with a mixture of 3 Gaussians, and then they would begin with, let's start with 1, 2, and 3 using the prior probabilities associated with the 3 classes. And given the particular class and the conditional distribution, generate a sample from that distribution. Would be one of these points. Well, that's this. And similarly, ancestral sampling means this is what's called as a Bayesian network. In a Bayesian network, we have nodes that are parents and nodes that are children. And we start with the parent value being set to one of the values possible. And then given that, you generate one from the conditional distribution P of x given z, and that's how you generate the data. So anyway, this is an aside here. They had a data set like this, and this slide was only to say how did they get that data set, and this is what they did: ancestral sampling. And so they compute the responsibilities gamma of z and k associated data point xn and component k, and this is what constitutes the class that is going to be determined for a data point. Colored, it says for a data point gamma of z and k equal to 1, it is colored red, and Zn equal for another point, it has equal blue and green. So these responsibilities determine the color. Is it one color or is it 2 colors, and so on. And all of this is being formulated as a maximum likelihood for a Gaussian mixture model. And that Gaussian mixture model is being represented. Unfortunately, this is a topic we haven't covered yet. This is what I usually cover in 674 in terms of probabilistic graphical models. Those of you who are planning to take 674 next semester, you'll learn some of these kinds of things. This is what's called as a plate representation over samples n going from 1 through capital N, and each of them have this relationship that there is a parent variable and a child variable, and the child variable is the data that is known, and we don't know the assignment of the data to the parent, which is the class, which is why this is kept open, this is kept closed, saying this data is known, this data is not known. And these are parameters. Pi is a parameter influencing this, and then mu is a parameter influencing this. Sigma is a parameter influencing this, and there's a parent-child relationship between the class and the. Okay, anyway, that's Gaussian mixture model representation, and we move on from there to talk about the mixture density function, and from then we move on to the likelihood function. Now that we know, if you have any probability distribution, we can multiply independent samples n equal to 1 through n, so that becomes the mixture likelihood function. Log likelihood function is this, and we would like to maximize this. A more difficult problem than for a single Gaussian, of course. So it involves a logarithm with a summation as an argument for the logarithm. It gets complicated here, which is why there is no closed form solution to this mixture of Gaussian's problem. And goal is to estimate 3 sets of parameters: pi k, the responsibility for the kth point; mu k is the mean of the kth cluster; and this is the covariance matrix here. So goal is to estimate 3 sets of parameters. That is the importance of the component. I should say this is not for the point, but for the class, right? The importance of the class. And so this is what we have to determine. And a gradient based optimization is possible, and we use for it the iterative EM algorithm. And so the algorithm here is a generalization of the k-means, which we just saw, which is a simple algorithm. This one involves this pure form of expectation maximization. And there are all kinds of issues of singularities with Gaussian mixture, whether it can be identified or not. Let's keep that part. Identifiability, is it possible to uniquely say, is it A, B, C, or is it B, C, A, and so on? Those are all interesting issues. And this illustrates the expectation maximization for Gaussian mixtures. And it sets the, we see there was some optimization going on in the expectation maximization we saw for k-means. Same thing here, which is where the derivatives come into play. And EM for Gaussian mixture model, it talks about all the derivatives that are needed here. And then the maximum likelihood solution for the means it is computing. We saw that there was a step where maximum likelihood for the means was computed in the second step. First step was expectation for the assignment of the gamma values, and similarly maximum likelihood for the covariance and mixing coefficients, that is what is the importance of each of these. And so the Gaussian mixture model for maximum likelihood parameter estimation gives the values for the means, covariance matrices, and all three are in terms of responsibilities. And so the EM formulation is first choose initial values, the means, covariance, mixing coefficients, alternate between E step and M step. In E step, you use current values of parameters. In the M step, use these posterior probabilities to estimate means, covariance. So this is the overview algorithm is fairly straightforward. Again, in E and M step, and the E step use the current values of the parameters, and the M step use these to estimate means, covariances. And what they're doing here is applying EM to the same data set we saw with the old faithful. Previously, we saw k-means, what it did. And here we have EM, which is data points of initial mixture model. So we're starting with some distributions here, and then we keep on improving it. Initial E step and M step, and after 2 cycles, 5 cycles, after 20 cycles. So what we are doing here, then before the assignment of clusters seems similar, except it's a soft clustering that we get the values for these points as to what they belong to. Comparison with k-means. K-means results look like this. EM result looks like this. So it's almost the same, except there was this one blue point here, it became red here. I guess that's the only difference. Yeah. So there is an animation available to this. You can take a look at it. Anyway, I'll let you take a look at it. There it is. How the EM algorithm goes about figuring out the clustering. I guess it's repeating again and again. EM Old Faithful. So EM takes many more iterations than k-means. Common to run k-means first in order to find suitable initialization. And covariance matrices can be initialized to covariance of clusters found by k-means. So they're saying use k-means as the first step. And then use the means found as the initial points for the, and then the covariance matrices of those. And then you use EM. Right, this is again summarizing this whole thing. It's a bit complicated, but what are the main steps? E step, M step. Okay, that is a pretty involved thing to get through the GMM version, but you can see that the method is more robust, so worth taking a look. If you're doing project 2 using k-means and want to be ambitious, go on to EM. You might find some, good implementations of it to use and try it out and see how well it does for you. Okay.